All right, so this is the method of cylindrical shells, and this is our last method. So what's going to happen is we will have a rectangle, and as we rotate this rectangle, it's going to make this cylindrical shell. Now, if you remember, our dr here is our thickness, but it's the limit as n is approaching infinity, which is making these rectangles super thin. So you can basically just think of it as a surface area. That's one way to look at it. So our circumference here is 2 pi r. And then as we stack that all the way up through this problem, stacking those circles, we get 2 pi rh. So it's the surface area of the cylinder is what you can look at. It's like a really thin piece of pipe where that wall thickness is so thin that you can almost not see it. It almost becomes transparent. And another dimension that we're going to get here now is we're going to introduce a radius. And so as we place that rectangle and rotate it, that radius is x. So the radius of our cylinder is going to be x. The height here is going to be our y, just like before, so our f of x. So if we take that volume idea and we plug everything in, it's 2 pi x f of x change in x. So we get this as our basic formula. Now that's just the basic formula. It doesn't always work. You do want to think about these as our shape. So we're going to be drawing the shape each time as we do this and then creating the formula. All right, so let's take a look at one. So we're going to find the volume obtained by rotating about the y-axis, the region bounded by y equals x squared, x equals 0, and y equals 3. So here is our picture. There is our y equals x squared, there's our y equals 3, and there's our x equals 0. So we get this region, and we're going to rotate it about y. Now with shells, as you rotate about the axis, the rectangle that you draw will always be parallel. So these are always going to be parallel with shells. They're perpendicular when we do discs and washers, parallel with shells, and this is why. So as we rotate this about the y-axis, you see what shape it makes. So our rectangle here, which has a thickness of dx and is a y equals, every time we draw the rectangle and we use shells, it's going to be giving us our height. So this is always our height, whatever letter we place there. So we can come back up now and draw what we have. This is y equals 3. And then this is y equals x squared down here. So you can see that the height is the difference between the two. So we know that our height here is 3 take away x squared. Now going back to our picture before, you can see that the radius of our shell is an x. So if I come down here and I draw a little blue line, you would notice that that is our x coordinate that we're plugging in right there. That is x. So we know our radius is x. And our volume is 2 pi r h. Right? I don't want to put the dr on there, or the dx in this case. I just want to make a nice formula that we can plug in so that we can use our basic formula before, where we know our thickness is here, and then we're just going to plug that in here. So 2 pi x 3 minus x squared, and then that would become what we need. So if we do a quick little distributing, that's 2 pi, and we're going to put that outside. This would be 3x minus x cubed. So that goes over here, 2 pi 3x minus x squared. So before we were plugging in the area, and we plug it in, it's the same basic idea. We're plugging this in here. So this is the area of our shell. So it's not actually a total volume yet. It's just the area that we get. So this is our surface area. We plug that area in, and we can use the formula we did before. Now what we need is, remember, these values that go here and here, your a and your b, your start and your finish, always reflect with that x. So this is dx, so we got to look at the x-axis. So obviously we know we're starting at 0. But now again, we need to find out that point of intersection so we know where it finishes. So we know we start at 0, but we need our finish. So if we take our x squared and we set it equal to 3, there you go. Now obviously it's plus or minus. We want the positive one. So square root of 3, and there you have it. So this will give us the volume that's created. Let me show you what's happening before we do that. So you can see this is our rectangle, and we know it's a good rectangle. So remember, if we move it back and forth, it's the same thing. It's always 3 take away x squared all the way through the entire shape. And then now if I rotate it, you can see it's making that cylinder. And then as we take it from 0 to rad 3, it's going to take that cylinder through the entire thing. So you can basically think of it like wrapping paper. We're going to make one tiny cylinder and just keep wrapping pieces of paper around it in a cylindrical shape all the way until it gives us that. So all of these cylindrical pieces of paper wrapped together will create the solid that we want, which is given in that picture. And so if I move it back a little bit, we can kind of see this. There is our cylinder. And so it has a radius of x here. So wherever the x coordinate is, that is going to be our radius, whether it's there or here. So if you plug in any x value like 1, that's going to give us our radius at 1. So like that, x equals 1, we'd have a radius of 1. At 0.5, our radius would be 0.5. So our x coordinate here represents all those radiuses. And then there's our basic rectangle there as well. And so you can see at the height is our y coordinate, which is f of x. So that would be 3 take away x squared. And that the thickness is dx. And so we get everything we need. So it's 2 pi rh. That's our circumference times the height. And so we end up with 2 pi x and then 3 minus x squared. So we're just plugging in an r and an h each time. You're just figuring out what is the radius, what is the height, and the height is the rectangle itself. So it's just the same thing we've been doing, which is top take away bottom. Goes right in there, and there is our area. And then now all we have to do is use our integral. So from start to finish. So from 0 to rad 3, that would give us every single cylinder with those dimensions. So as we plug in the x, it's giving us every single cylinder. We plug in 1, it gives us the area of this one, and then the area of that one, and the area of that one. And so just all these surface areas tacked together to give us our total volume. And just checking, that was supposed to be a 3. So this gives us 9/2 pi. There you have it. All right, now let's try it again, but now we're going to rotate this about the x-axis. So we do the same thing. This is the only options, x and y right now. And so our rectangle has to be parallel with that axis. So we draw our rectangle here, and then we rotate. And so there is our shell. And so you can see that the radius here is now the y coordinate. This has a thickness of dy, and then the height here now is the x equals. So we have to go back up and solve this for x. So the only function that we have that we're getting the area between is going to be this function, take away 0. So we don't have to worry about taking away 0. It's just the area under the curve with respect to y here. So we just need to solve this one for x. So if we solve it, x is the square root of y. That's our positive side. This is the square root of y. This would be the negative square root of y. And all we're dealing with is the positive. So that one. So that means our height here is the square root of y. So if we plug this in, our h is square root of y. Our radius is y. And so then our area would be 2 pi r h, which is 2 pi y square root of y. And there we have it. So now we just need our integral. And again, it's dy, 2 pi y square root of y. We can combine those together and do it by hand, but we're going to use the calculator here. And so our y values, the starting y value would be 0, and the finishing y value is 3. So remember, we always pick it off the dy, so that's 0 to 3, which gives us 39.178. It's obviously not exact, so if we want the exact, then we're going to have to do it by hand, like this, which would be 36/5 pi rad 3. So there's all the work for that. But I'm fine with 39.178. And then if you rotate the shape, you can kind of see it's that inverted shape here. And if we go back and rotate this one, it gives us, whoa, way too far there. It gives us that solid that we had in the picture. But that's all it is. You just want to think about finding that surface area, and then you're just gluing each of these surface areas together from 0 to 3. So it's just 2 pi r h, and there's your two rotations, one for x and one for y. Well, y and x. Thank you.